Hi, I'm Dr. Jonathan Reichenthal, and this is my masterclass, The Rise of Digital Twins in the Fourth Industrial Revolution. You know, we've been through many different types of industrial revolutions since the 1700s. In fact, the first one was about the introduction of steam and how steam enabled mechanization. And this was quite a significant transformation for humanity because we went from things being powered by people and animals, and sometimes with wind turbines, to having steam powering things. And so that meant we could have much more complex mechanical processes, which enabled factories. And the factories started to produce products in high volumes. And almost less than 100 years later, we entered a second industrial revolution that was characterized by the use of electricity, us leveraging that incredible science. And electricity started really contributing towards mass production at scale. And so now we had many, many more factories, and we had the introduction of the production line. And because of factories, more and more people moved from the rural areas and to be close to the factories, which really accelerated urbanization in the 1800s and was a major catalyst for the creation of great cities and mega cities today. In addition, electricity allowed us to have telecommunications, and with telecommunications, then we could create the information technology revolution, which really is the third industrial revolution. But before I speak about that, let's talk about the origin of the real information technology revolution. It starts because of a satellite that the Russians send into space. In 1958, they send Sputnik up, and it flies all over the world, crosses across the United States. And in the United States, the conclusion is the Russians are ahead, and we need to have technology that can compete. And so lots of investment went into the technology to have an American space program that could compete and go ahead of the innovation that the Russians and the Soviet Union at the time were implementing. And so lots of money went from the federal government in DC across the country, but particularly into the West Coast around the Palo Alto and sort of North California area. And that investment really resulted in the creation of what is now today Silicon Valley. And why it's called Silicon Valley is because the technology necessary for satellites and for better rockets and for the space program is really found in very, very small switches called transistors. And to make them really, really small and to use electricity to enable those switches to be on and off and to power computing, one of the best materials we could use was semiconductor material. And the semiconductor material that was used was silicon. So it became known as Silicon Valley. Of course, the rest is remarkable. We started a multi-decade revolution that introduced all sorts of technologies and connected the world, enabled the internet, and thus was the third industrial revolution. We really are at the beginning of this third industrial revolution. Our smartphones, our connectivity, all the innovation and efficiencies that are created from the internet, they're remarkable, but we still, I think, have a long way to go. It's worth remembering that only half the world has access to the internet today. So we still have another 3 billion or so people to bring online, and when that happens, we'll get into a subsequent level of maturity in the internet. And so what strikes us now is, as we enter sort of the 2020s, is there seems to be a nexus of pretty big game-changing technologies. Whether it's now entering the next generation of the internet, or big data, or artificial intelligence, even quantum computing, it feels like we are entering yet another type of revolution, completely enabled by very much game-changing technologies, but also things like changing economics. We have greater globalization, We have new science that's introducing things like new materials, like graphene, that are changing how we can build and produce products. Advances in medicine and shifts in demographics, where we see some countries aging quickly and other countries having very, very large young populations. For example, on the continent of Africa, a big proportion of people there are under the age of 20. Whereas if we look at countries like Russia, even the United States, and different areas in Southeast Asia, we have average populations in the sort of 30 to 40-year age group. And those differences will make a difference in how the marketplace operates and who embraces technologies in the years ahead. So it really feels like if you bring all these different macro trends together, that we are in a fourth industrial revolution. And so what does that revolution look like? What are some of the characteristics? I'd like to share with you 4 brief criteria that should help us think about why it's different from the third industrial revolution and previous revolutions to that. The first characteristic is this notion of scope, that when new technology is implemented, it's used and adopted by not thousands, even hundreds of thousands of people, potentially millions of people very, very quickly. You look at the rollout of the smartphone, and the smartphone gets into the hands of 50 million people in just a few short years, less than 10 years. A game like Pokemon Go, a very popular game, gets into the hands of 50 million people in 19 days. So the scope of how we are deploying technology is not only quicker, but much wider and global more quickly. The second characteristic is this notion of impact. And what we mean by this is when we get new innovation into the hands of millions of people, maybe a billion people, that can have very significant consequences. Both positive, hopefully, mostly positive, and potentially negative. When a line of code is changed in Silicon Valley on a Tuesday morning, by Tuesday afternoon or Wednesday morning, it can impact billions of people around the world. Think about, for example, the deployment of a new operating system for a smartphone for, let's say, Apple or for Android. And we can implement and deploy that operating system in just less than a day to a billion people. And the good news is if we are rolling out new capability, it gets into the hands of that many people that quickly. Equally though, if bad software is deployed, it gets into all those people's hands too, and that can be quite complicated. The third characteristic of the fourth industrial revolution is the speed. Now we all feel it. We all feel the speed of new capabilities, new applications, new upgrades. We all know that when you're getting used to your phone, there's a new version of your phone coming out. Or you get used to the features of an application, and there's a new version that changes how the application works. Once again, when a new capability arises, that capability can get into lots of people's hands very quickly. And we've never really had to deal with that before. There is no precedent to that. Think about 100 years ago or 200 years ago in the original industrial revolutions, things moved, but they moved slowly. Today, when somebody has an idea and they write some software, 50, 100, 500 million people can get that software potentially within hours if it's deployed in a certain way. And then finally, the fourth characteristic is this notion of convergence. Now, it's very important to think about technology like artificial intelligence on its own or blockchain technology on its own. But even more valuable today is what happens when you intersect, when you connect these technologies together. What happens when you use quantum computing with blockchain technology and artificial intelligence? When we intersect those things, we get new outcomes and new solutions that are today actually difficult to even conceive of. We have to do the work, we have to innovate, we have to experiment, and then we find out. A big game-changing industry like the on-demand car markets, where we can summon a car just with our smartphone in less than 5 minutes. That innovation really started around 2010 when it started to be embraced in a big way. And And it's not a surprise, because really what happened in 2010 wasn't that we discovered this idea or we created some groundbreaking technology. It was the convergence of technologies. The convergence of GPS, prolific smartphone use, big data, artificial intelligence, social computing, online payment systems. It all had to come together, it had to converge. And then you get incredible on-demand services like we have today. So those are the 4 characteristics. There are more to know about this. There is more to know about this. But this is really the core framework by which we can think about this 4th industrial revolution. Now, this 4th industrial revolution really ties in closely with a different categorization scheme, and that is the specific industry or industrial changes that happened and occurred at the same time as each of the 4 industrial revolutions. Industry 1.0, 2.0, 3, and 4.0 are all subsets, the industrial end of these revolutions. And so as you can see, Industry 3.0 maps directly with the 3rd industrial revolution, which really was super focused on electronics and the information technology revolution. And now, in the 4th industrial revolution, we have the rollout of a whole new set of tech in what is called Industry 4.0. And in Industry 4.0, it's all about remarkable new innovation that is changing how we build things in our factories, how we can improve and run more efficient production lines. Here you have a picture of a factory that's building cars. In this picture, the robots can predict when there's going to be maintenance issues. This is really helpful. And then if there are maintenance issues, the robots will fix themselves. So that's why there's only 2 people in this picture, and I'm not sure what they're doing. But the 4th Industrial Revolution and Industry 4.0 is very much driven by much smarter factories and much smarter. And one characteristic of this, one big emerging field, is this idea of creating digital twins or virtual replicas of physical things to make the design, manufacture, and operations of factories be much better. And so that's what I want to explore for the next few minutes, is what is the role of digital twins in Industry 4.0 being a subset of the 4th Industrial Revolution? Well, we're going to look at it through the lens of 3 different phases of what's typically the product lifecycle management process, PLM. You've got 3 phases at a minimum: design, build, and operate. There are more there. There's planning, there's optimization, there's the retirement of products. But the core areas that you need to think about right now are design, build, and operate. And so what is the role of digital twin in each of these? And I'll just share with you a few examples here to get our minds wrapped around the value that a digital twin brings to the product lifecycle management process. And so for design, here I illustrate how we're using a high-performance computer with intense processing power, very good visualization, and the adoption and the use of a lot of data to render a future car. And so one could argue, well, that's not terribly new. Well, what makes this new is that not only can we design this car with great precision and both historical data and projected data, but we can now run it through almost every conceivable scenario. So things like, how will the car respond to wet conditions on the road, or extreme cold or extreme heat? What are the stresses on the different materials we use in this car? So that we can start to explore as engineers whether there are better materials to use or to swap out, different design elements. So engineers and designers and a whole range of stakeholders now can design much more superior products and do it faster than we've ever done it before. So this is what we call a digital twin. We haven't built anything yet. We've simply rendered a digital version of what will be, hopefully, a physical object at some point. We're using some really great software, some really high performance processing, artificial intelligence, lots of data, and great visualization to get to this design. it's greatly informed by a range of data sets. And this helps the designers make important decisions over time. Now we go from the design phase, now we're ready to build something because we've completed all our tests, we've run all our scenarios in design, and we're ready to manufacture. So now we want to create a digital twin of the manufacturing line, because we also want to simulate what that will behave like and create the most optimum production line for this car. We'll keep with that example. And so a digital twin can be created for the entire production line, as you can see in this picture here. And we can experiment with things again like some different types of mechanics, different types of materials. We can also evaluate costs and trade-offs. Now, not only do we have a digital twin of the design, but we have a digital twin of the production line. And from both of those, we can now start to produce the physical product. The digital twin technology is able to deliver us the specs on both the product we're going to build and the manufacturing line. And those specs can be distributed to a whole range of stakeholders, vendors to provide the materials and different parts and the different chemicals that will be needed in the processes. So it is a large ecosystem of participants who benefit from this digital twin ecosystem. And then finally, we move from design to build, the product's built, goes out to the world, and now we want to be able to maintain it better, to operate it better. And for this example, I'm using a wind turbine. So imagine for a moment this wind turbine is some distance away. It's being built through the digital twin process, and now it's deployed in the field, and we want to monitor it. So we will cover this turbine with a whole lot of sensors. These sensors will collect critical data. The data will be sent in real time back to workstations that will be available for engineers to evaluate what's happening at any moment in time. What's the weather? How is the wind turbine performing? Is there any vibration? What's the heat? What are the heat issues? Is it working optimally? Is it stopped working? So this data from these sensors being sent back from the physical object to the digital object gives us this real-time information so we can make decisions. Now back at the workstation, the engineer can determine perhaps the wind turbine is not performing optimally, so some configuration changes we made. We can even simulate our changes before they are sent to the wind turbine. But once we're happy with the configuration, we can upload that data from the virtual twin, the digital twin, right up to the physical twin, in this case the wind turbine, and then it'll get the software and the data and be able to, one hopes, perform better. And so here we see an illustration of a wind turbine. It's just a sort of just to show you that each of the physical elements can be linked to a virtual twin here, and at the bottom we can interpret and be able to consume a range of different information points about this particular wind turbine. It's not just about manufacturing though. What's amazing about digital twins is they are being implemented in a whole range of industries. And for example, it's been used, beginning to be used in healthcare. And we're able to use, for example, we see this picture of a virtual hospital or a virtual version of a physical hospital, where we can do things like look for efficiencies and processes. We can monitor all sorts of equipment. Now today, hospitals are very sophisticated entities with a lot of technology. We can look at things like the intake of a patient right through to a surgery and then evaluate outcomes. So we can implement digital twins comprehensively across the healthcare network. It's just one additional industry as an example. Digital twin data doesn't have to be just visualized. It can be in the form of dashboards. It can be in the form of just reports. It's going to depend on the stakeholders. It's going to be a lot of different type of people who want to be able to review information sometimes after the fact, sometimes in real time, sometimes comparing data over different periods. So we need to acknowledge that one of the most valuable outcomes of a digital twin ecosystem is the data that is created from it. We also need to recognize too that in the digital twin ecosystem, we not only accept data, but we also put data into the system, often historical data, to be able to help us with things like design, and then also help us with maintenance goals. So we have some goals to go after relative to historical data. Now, in a digital twin ecosystem, when it gets sophisticated, there's going to be lots of stakeholders. There's going to be lots of geographic areas that are connected together over wide area networks. And that also means there are more attack vectors. There are more chances to steal what is often very valuable data. So it's important that we are focusing on the cybersecurity elements. And within this topic, I recommend very much that the student of digital twins, very much emphasizes and prioritizes cybersecurity. We have to make sure that the data that's been used to design our product, which is often going to be, very valuable intellectual property, is protected. That only the right people are able to access certain features of the system at the right time, and so cybersecurity needs to be at the top of the priority list in how people implement and run these digital twin systems. So what does the future hold? Well, this is growing very, very quickly. The statistic right now, even in the manufacturing space, is that 50% of major manufacturers in the world are utilizing digital twin technology. So it's already adopted quite largely, and it's quickly finding its way into areas such as healthcare, into smart cities, into financial services, and a whole range of design industries. So this is going to be a very big topic over the next few years, and a fundamental piece of the fourth industrial revolution, in particular Industry 4.0. I highly recommend that a very large range of stakeholders and people's careers within those groups, that they begin to learn about this technology, make it part of their portfolio of knowledge and skills, because it's going to be really valuable as we progress through this remarkable. Thank you very much for listening to this masterclass. I hope it sort of gave you an idea of the basic concepts and why this topic is already important and becoming very important in a wide range of industries in the future. If you're intrigued if you want to know more, I would encourage you, and I hope you really will take advantage of a new course that I have called Introduction to Digital Twins with Esade. And I think that'll be a great way for you to get deeper on the topic, to explore a range of industries, to learn from different videos and different products and services what is happening in the space. I think that will really help you with your career. And if you're particularly interested in becoming an expert in digital twins, this is a fantastic starting point. So I hope you'll take advantage of that, and I wish you all the best and good luck in the future.